Okay, lecture 83, Bernoulli's principle. So Bernoulli's principle is interesting and it's a little bit non-intuitive. Let me explain what I mean. So we'll notice that in a pipe of different diameters, the liquid will flow at different speeds. This is kind of intuitive to you if you've ever used a water hose, right? You put your finger on the end of the water hose and the water comes spraying out with a much stronger stream, right? But what is a little surprising is that the pressure in the region where the velocity is greater is actually lower than in the region where the velocity is lower. So here, the liquid moving through the pipe, right, will be moving very fast, and then here it will slow down, right? So if you've ever been to a river, right, this is what rapids are. You've got a nice deep river that's flowing at a steady rate, and then it runs into a region where it's very shallow and there are lots of rocks around, and you get these rapids, right? The water moves very swiftly then, okay? If we were to put some bubbles, right? A bubble, what is a bubble? A bubble is basically, it's created by surface tension, okay? So if you put a little soap in a little bit of water and you mix it up, you can make basically bubble mix. There are better ways to make it, but glycerin, for example, is a great way to make bubbles. What's holding the bubble together is surface tension. It's like a balloon. Inside there is air that has some pressure, okay? So if the pressure is constant, right, think of a balloon, right? If we take a balloon, which at atmospheric pressure is, say, this big, if we move it into a region where lower than atmospheric pressure, right, if we evacuate the container that it's in, for example, you'll see the balloon bulge out. Why is it doing that? Well, because you've got pressure inside the balloon that's pushing out in all directions, right? And inside the container, the pressure is pushing in from all directions. If these balance out, for example, then it'll stay at a constant volume, right, or a constant size for the balloon, okay? But if I decrease the pressure on the outside, or conversely increase the pressure on the inside of the balloon gets bigger, okay? It kind of makes sense, right? Well, if we move bubbles through this pipe, what's going to happen? Well, we'll see that here, where the velocity is very high, the bubbles might be very large, for example, but as soon as they move into the higher pressure, slower moving section of the pipe, the bubbles become small bubbles. Okay? So this relationship between the pressure and the velocity is what we're trying to get at today. Okay? As a consequence of that, it has far-reaching consequences. One of them is the concept of lift, right, which is the physics of flight. So if I take a piece of paper and I allow some air to move quickly over the top of it, right, there will be a force from below, which we call lift, because it's a pressure imbalance. Under here, the air is moving more slowly, and so the pressure is greater. Up here, the air is moving more quickly, and so the pressure is lower, and you end up getting lift, which lifts it up. That's what makes airplanes lift up into the air. So let me just demonstrate it real quick. I'll just blow over the top of this piece of paper. See? It lifts up. Let's just jump right into it. We're going to prove this, or demonstrate this, or maybe derive this Bernoulli's principle by using the work energy theorem. Okay? I forget what lecture it is that we talked about that in. I'm sure I'll post it in the video. But and the way we're going to do it, we're going to look at, let me just draw it like this. I want to look at a fluid moving through a pipe at two different times. Right? We'll call this one T naught. Here's my pipe. And the left wall of this fluid that we're considering will be right here. And the right wall of this fluid that we're considering will be right here. So this is this part of the fluid that we're going to consider mathematically. Okay? And at some time later, T1, these walls will have moved to, say, here. Okay? Do you see what's happening? So we're going from a certain amount of liquid, right? Going from here to a time later going to here. Right? This is just another picture. You can see the left wall has moved some distance. The right wall has moved a smaller distance. Okay? So I can try to draw that in one picture. But now that you see the concept of it, what it is that I'm talking about, I think it'll make sense. So here I'll track the left wall, and this will be the right wall as a dotted line. Left wall is a solid line, right wall as a dotted line. Okay? So it's moved. We'll call this delta x1, and we'll call this delta x2. Okay? So what is it that moved it? Well, so we assume that the velocity is going in this direction. All right? if it moved, right, that must mean there was some pressure pushing from this side. We'll call that P1, or what actually, for now anyways, we'll call it F1, okay, a force pushing to the left, yes? But we'll also have a force, F2, resisting that motion, pushing to the right. All right. This is pushing to the right, this is pushing to the left, okay? So it's the balancing of these two forces. If these two forces are equal, the liquid obviously is not going to move anywhere, right? Since we're assuming that the velocity is in this direction, then this force must be greater than this force, okay? But let's also talk about, let's look at the cross-section of this pipe, right? If I take a cross-section of this will have to be, you know, say it's a circular pipe, and we'll call the cross-sectional area A1, okay? Whereas with this pipe, the cross-sectional area is obviously much bigger. It gives more space. And that will be A2. Make sense?
Yeah.
Okay. So we can write that F1, I want to re-express these forces in terms of pressure, okay? Well, pressure is just force divided by cross-sectional area, right? So that's P1 divided by A1. And similarly, F2 is P2 divided by A2. I probably want to put a negative sign in there to show that it's pushing in the opposite direction, okay? So what is the work? Well, the work is, of course, force times distance, right? So we can write that as P1 over A1 nope, not over A1. Whoops. Oh, I totally messed that up, didn't I? Whoops, sorry about that. I got the F's and the P's all backwards. Pressure is defined as force divided by area, right? Not the other way around. So this is P1, which is F1 divided by A1, and P2, which is F2 divided by A2. So yeah, that looks better. So then this force times the distance, right? We have two of them, right? We'll have F1 delta x1 minus F2 delta x2, right? That's the work, force times distance, right?
Yeah.
Well, we can rewrite that in terms of pressure as P1 times A1. If I multiply this times A1, I get F1, right? Times delta x1 minus P2 A2 delta x2. Okay? So far, so good? But this, of course, is just, let me just write it down here. P1, A1 times delta x1, well, that's just the volume, right? That's the volume in this little section right here, right?
Yeah.
It's a cross-sectional area times this distance, delta x, right?
Yeah.
So we'll call this V1. Similarly, this will be P2 times V2, okay?
All right.
Now we're going to digress for just a moment and talk about current, okay? Current is, we usually call it I, and in this case will be equal to some little delta M over delta T. It's the amount of mass that moves through per time. So if I had like a scale and a stopwatch, and I was measuring the weight of the water that came out in a certain time interval, like say in 1 second, right, I might say, oh, that's a kilogram per second. You see? That's the flow rate of the current, okay? Now, if we have what's called steady state flow, so what is steady state flow? That means that the pipe is completely filled with water, right? The water is moving with some velocity, okay? And it's not collecting anywhere or bunching up anywhere, right? Whatever I put in on the right side comes out on the left side. So the idea is that in steady state flow, the current in is equal to the current out. So that's the steady state condition. So the steady state, I'll call it SS for steady state, okay, says that I1 equals I2. So the current in from the left is going to be equal to the current in out from the right, okay? And further, I can rewrite I, delta M over delta T, right, as rho times V, volume. I'll put little bars on top of my volume, on my V for volume, since we have a V for velocity here as well, okay?
Okay.
Since rho is the density, and that's the mass per volume, then I can replace this delta M with a rho times a volume, okay?
Yeah.
And that will be still divided by delta T, but volume, of course, is just the cross-sectional area times the distance moved in the pipe, right? So I can write this then as rho times A times delta X over delta T, and Well, what is delta x over delta t, right? The distance, the displacement divided by the time it took, that's just velocity, right? So replace that with little v. Actually, I'll make it a vector v just to distinguish it, okay? That's the velocity. So we can write that the current is equal to the density times the cross-sectional area times the velocity of the stuff in there, right?
Yeah.
The stuff is moving through faster, bigger current, right? We'll get more liquid out, right?
Yeah.
Okay, so I1 equals I2. That means that rho 1 times A1 times V1, the velocity 1, is equal to rho 2 times A2 times the velocity 2, right? So the density times the cross-sectional area times the velocity will be equal to the density here times the cross-sectional area times the velocity there, okay?
All right.
But this is a liquid, right? And a liquid is an incompressible fluid, right? I should just note, by the way, that Bernoulli's equation also applies to gases, okay? Gas can be thought of as a compressible fluid. Sometimes it used to be called an elastic fluid, where fluid kind of captures both liquids and gases, whereas liquid is specifically the state of matter, which we know is liquid form. Make sense?
Yeah.
So if I say fluid, remember that there are compressible fluids, which are gases, and incompressible fluids, which are liquids, okay? Generally speaking. But since this is a liquid we're talking about, because we're still on the liquids, right? Rho 1 and rho 2 are the same, right? Because they're incompressible. Yes?
Yeah.
So the density doesn't change. The density over here is the same as the density over there, right? Because it's a liquid. And liquids are incompressible. So we can kind of get rid of that, see? And so we get this nice relationship that the area, the cross-sectional area here times the velocity is equal to the cross-sectional area over here times the velocity over there, you see?
Yeah.
And I'll call this star 1 because we'll use that in just a bit. But we can take this just a bit further. I'll just digress here for a second because I want to talk about V1 and V2, where these are volumes, remember, so I'll put the little hats over them. This can also be written as A1 times delta x1 over delta t equals A2 times delta x2 over delta t. The delta t's are common to both sides, so I can just cross-multiply them away, yes? And what do we get? We get this. Well, this is just V1, right? And this over here is just V2. So we get that V1 is equal to V2. So the volumes are the same. So I can write this instead as the quantity P1 minus P2 times V, where V is equal to both V1 and V2, okay? And this is called the continuity equation, by the way. I don't know if I said that. Star 1 up here, this is the continuity equation. It's generally true for steady state systems. All right, so back to this now. Well, this is only one half of the work energy theorem, right?
Yeah.
This is the work that we did. This is P1 minus P2, that's just a delta P, okay? It's the change in the pressure from here to here, okay? The other half of the work energy theorem is the kinetic energy, right? So the work energy theorem says that this work is equal to the change in the kinetic energy. So we can write that out now. And the change in the kinetic energy, ooh, thunder. The change in the kinetic energy would be 1/2, we'll call it m1 times v1 squared, that's the velocity. Actually, usually we do final will be over here, initial will be over here, so we'll have m2 v2 minus 1/2 m1 v1 squared, okay? Kinetic energy over here minus the kinetic energy when it was over here. Make sense?
Yeah.
So if these two are equal, right, then we can write that P1 minus P2 times the volume is equal to 1/2 m2 v2 squared minus 1/2 m1 v1 squared. If I divide the mass over here by volume, what does that give me? What is mass divided by volume? Anyone remember? Say it?
Density.
Density, yes, density. So I'll divide that volume here on both sides, and that will just replace m2 and m1 with rho 1 and rho 2, but they're the same because it's a liquid. So we'll just call it rho. And we don't need the parentheses anymore. So P1 minus P2 is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay? At this point, and we can call this equation star 2. And this is one form of Bernoulli's equation. His more general equation also includes gravitational potential, and we'll look at that in just a sec. But let's follow this through, okay? So I want to now use star 1, right, the continuity equation, in here to get rid of one of these components of the velocity. Probably the best one to get rid of is v2, because v1 you can think of as kind of an initial velocity, right? This is what the velocity is over here on the left-hand side. So we can solve this for v1, or excuse me, v2, to get that it's equal to a1 over 8, oh, it's right here. v2 is equal to a1 divided by a2 times v1. And so if I substitute that in here, I'll get that p1 minus p2 is equal to, getting closer, 1/2 rho. And I'll replace v2 with this v2 from the continuity equation. So that's going to be a1 squared divided by a2 squared times v1 squared. But look, we've got a v1 squared over here as well, so I can factor out a 1/2 rho, right? And I'll get a1 squared over a2 squared minus, this will just be 1 times v1 squared. Okay? So what does this tell us? Well, if we look at this, we see that a1 is less than a2, yes?
Yeah.
That means that delta p, if we look at it here, right, if a1 is less than a2, what can you say about a1 squared over a2 squared, right? This is less than 1, right?
Yes.
So something less than 1 minus 1, of course, is negative, right? So we get that delta p is less than 0. That means that the pressure has dropped, right? If the pressure has dropped, that means the pressure was higher over here. Did I say that right? No, I'm sorry. I got that completely backwards. If it was higher over here, it would be a positive change in pressure, right? If the pressure is lower over here and the pressure is higher over here, then the change, of course, is negative, right?
Yeah.
So it's less than 0. So that's telling us that the pressure is, in fact, lower over here than over here in the wider section of the pipe, okay?
All right.
So that's the weird consequence that's kind of counterintuitive. Because, when you think about it, you think, oh, the fluid's moving very fast over there, so you feel a lot of fluid bumping into you. And so wouldn't that mean the pressure's higher? You see, that's why people get confused about it. Probably why I just said the wrong thing here just a minute ago. But to me, anyways, it's always been kind of counterintuitive that that's the case. I'm thinking, well, if I'm in my car and I roll the window down, and I stick my head out the window, right, I feel a force on my face, right? And since pressure is force divided by area, my thinking is, oh, that must be, an increased pressure. But if you think about it, what's the increase in the pressure there? That's the air, which used to be moving really fast. It's now stopping because it's hitting you in the face, right? So it's a bit weird. But if you're in a car and you roll down the windows, what happens to stuff in the car? If I've got some, I don't know, feathers for some reason in the car, are they just going to sit in the car, or are they going to go flying out the window?
You're gonna go flying out the window.
Yeah, and so your thinking is they got sucked out the window, but what's really happened is because the air is not moving inside the car, but it is moving outside the car, the pressure is high inside the car and low outside the car, and so everything gets pushed out because of this pressure differential, okay?
All right.
Let me see here. Anything else to say about that? Well, I guess you could just follow this through, since P1 minus P2 is delta P, and that's less than 0, that means that P1 is less than P2, which is what we were trying to find out. So that's the surprising result with that. Also, from 1, right, what do we know about the velocities here, right? If A1 is less than A2, right? So A1 is less than A2, how does V2 and V1 relate? So let's say V1 is 1, okay? 1 meter per second. Well, since A1 over A2 is going to be less than 1, that means that V2 must be what? Less than 1, so it's slower, right? So that's telling us, the continuity equation tells us the velocity in the wider section of the pipe is slower than the velocity in the narrow section of the pipe, okay? The concept that the fluid is moving faster in the smaller pipe than in the larger section of the pipe comes purely from the continuity equation. The notion that the pressure is lower in the fast-moving section and higher in the slow-moving section is a result of Bernoulli's equation, okay, or Bernoulli's principle, okay? Yeah. And so this also explains why the paper had the lift, right? Because the pressure beneath the paper was higher because the velocity was lower. On the top of the paper, we have the fast-moving air, the velocity is higher, so the pressure is lower, and that's what gives you the lift, you see? Lift is what makes airplanes resist gravity and stay up in the air.
All right.
Okay? So let's talk about the other part of Bernoulli's equation. That's the gravitational component, okay? Okay, this time around, I want to take a volume of liquid in a pipe. I'm not going to change the diameter of the pipe anywhere, so the cross-sectional area is always the same, okay? So we're removing that aspect of Bernoulli's equation. But it's a vertical pipe, and so we have gravity acting on this liquid, pulling it downward, right?
Yeah.
And initially, the top of the liquid is at some distance h naught, okay? And I'm going to very slowly, so as to give it, I want to do it so slow that the velocity is always roughly 0, okay? I'm going to lift this liquid up some distance. Maybe I should make a different color so we can see what has happened to the liquid. I want to move the liquid up, right? This delta x is going to be the same, right? Because this is the pipe is the same cross-sectional area throughout, right? It's a uniform pipe. And so this new distance, right, will be, call it h1, right? Oops, doesn't go that far. It goes, yeah, no, it does. It goes all the way to the bottom, right? So here we've created a change of delta x, which is h1 minus h naught, okay? But we'll just call it h. So this little change in distance here, we're going to call h. And we're going to let the velocity be 0. Now again, we'll have that p1 minus p2 times the volume is going to be equal to the gravitational potential, right? And how can we write that? We would write it as m times little g times h, right? That's the change in the potential energy that we've created for this little volume of liquid, right? I'm going to and so we can write that delta P is equal to rho GH, okay? So not much of a change there. That wasn't nearly as hard, it would seem, as was the first part where we consider the different pipe diameters, right? But let's do an example to try to understand this new term and what it tells us, okay? Okay, so you've seen a water tower before, yes?
Yeah.
The water is in this big container high up in the air, right? You're probably wondering why they put it way up there. Here we have a water container tower with a pipe running out the bottom to the ground level. We'll call this the ground level here. Okay? And the valve is closed, okay? So the velocity throughout here is 0, but there's going to be, we got this pressure at the top of the tower. We'll assume it's atmospheric pressure, okay? Which will approximate is 100 kilopascals, even though it's really more like 101 kilopascals. It's 101,000 newtons per meter squared, okay? And there'll be some pressure down here, right, at the bottom. We'll call it P sub V for P sub valve, okay? And if I open that valve, there'll be a velocity down here, okay? There'll also be a velocity up here, but it'll be very small because we'll assume it's a very big container. So if the water's coming out very quickly down here, you barely notice that the level's even decreasing up here at the top, right?
Yeah.
Makes sense, okay? Just to keep things simple. But if we put everything together, right, that we did before, right, we had that, we can write the full expression for Bernoulli's principle, right, which is that the pressure plus rho GH, that's the gravitational component, right, plus 1/2 rho V squared will be equal to a constant. Okay? So that's to say that, you know, we could make this, say, the top, and then on the other side would be equal to the same expression, but for the bottom. Okay? And that's what we'll do in this example. We need some numbers, though. So let's let P naught be equal to 1. I'm going to write it in scientific notation because it's easier to keep track of things. So this is 1 times 10 to the 5 newtons per meter squared. That's also pascals. Okay? Units of pressure. We'll let the velocity. Well, the velocity is 0 initially. We'll have to think about that first. The height of the water, right? How high is this tower, right? Up to the water level here. We'll just call that h, and we'll let h be 10 meters. Okay? So let's consider the situation where the valve is closed and figure out what the pressure is down here at the valve. So if we were to stick in a gauge, right, and measure it, this would tell us what the pressure is there. The velocity at this point, of course, is 0 because the valve is closed, the water's not moving, right? So what are we going to get? We'll get a valve closed, means that V at the valve is equal to 0, right? So we'll put V sub V means V at the valve, okay? So we'll write Bernoulli's equation for this. We'll have P naught plus rho GH. This term here, rho V squared, well, that'll be 0, right?
Yeah.
What is this value equal to? Well, P naught is 1 times 10 to the 5 newtons per meter squared. Rho, since this is water, right, this is 1,000 kilograms per meter cubed. G will approximate as 10 meters per second squared, and H is 10 meters, right? So 1,000 times 10 times 10, that's 100,000, or 1 times 10 to the 5, right? So this whole expression is 2 times 10 to the 5. And that would be Newton, we'll just call them pascals, P sub A, right? So what is that in like kilopascals, right? So if this is 100 kilopascals, then down here at the bottom, right now, this is going to be 200 kilopascals. Which makes sense because you got all this water sitting on top of you, right? Here at the top, all you have is the atmosphere sitting on top of you, yes?
Yeah.
Maybe this is an open container. So it's an open water container at the top. Collects rainwater or something, right? Make sense? That the pressure is higher down here than it is up there? All right, now what happens if we open the valve? So let's open the valve. Now we're going to get rho naught plus rho GH, which we already have this, right? We know what this is. This is just this 200 kilopascals that we just calculated. But we also have some velocity term, right? So plus 1/2 rho V sub valve squared. Well, we have to specify what that is. So when we open it up, right, let's assume that it moves at 10 meters per second. That's the flow rate, let's say, okay?
Okay.
So the speed of the liquid flowing out. So this part here, right, this is just the 200 kilopascals that we got before. What about this part here? Well, it's 1/2 times 1,000 kilograms per meter cubed times this velocity, right, which is 10 meters per second, but we have to square that, right? So that's going to give us 100 meters squared per second squared, right?
Yeah.
And so this will be 200 kilopascals plus, this is, my zero looked funny there. Looked like it was missing. We have 1,000 times 100, that's another 100,000, right? So this is 1/2. Well, it's going to be 50 kilopascals, right? And this should actually be minus. Where did I? Yeah, somewhere I lost a step, right? So for the open valve, we would have had that P naught plus rho GH is equal to P at the valve plus 1/2 rho V at the valve squared. You know, I messed that up, forgot to do that step, right? I went straight to this. We solve for P at the valve. What's the pressure at the valve, right? This right here. Well, P at the valve is just equal to this stuff. Well, that's right over here. Pressure at the valve is equal to P naught plus rho GH minus this term over here, right? The kinetic energy term. And so we get 200 minus 50, which means that it's now dropped to 150 kilopascals. Okay?
All right.
So that's the pressure drop that we see when we open the valve. Make sense?
Yeah.
Okay. That's what you can do with that. Sorry I messed up that last little bit there. Left out that one step. You kind of jumped ahead to the end, and hopefully it wasn't too confusing. But so that's Bernoulli's principle. Okay? I think we're done talking about liquids now, and we'll move on to gases next.
All right.
All right. That's it.